In the last class, we have seen how to calculate the regulation. This was the formula which we have derived, and this is the expression for calculating the efficiency of the transmission line. Now, in order to determine the ABCD parameters or the transmission line parameters, as in the case of short transmission line, we have seen that in case of short transmission line, in order to get the transmission line parameters or the ABCD parameters, we have to express the sending end voltage Vs and the sending end current Is in terms of the receiving end voltage Vr and the receiving end current Ir. So our aim will be to represent the sending end voltage in terms of Vr and Ir. Similarly, the sending end current in terms of Vr and Ir. Here you can, this is the equivalent circuit, and in T representation this is the equivalent circuit and this is the phasor diagram. So in order to find the ABCD parameters of the transmission line, so we have two sets of parameters Vs and Is, the sending end parameters voltage and current, and the receiving end voltage and current Vr and Ir. And it will be in the transmission line parameter, the representation will be Vs Is as a column matrix that is equal to the ABCD parameters or the transmission line parameters, and here you have Vr and Ir. So here you can see that Vs can be written as Vs is equal to AVR plus BIR. Similarly, Is is equal to CVR plus DIR. That means say Vs is equal to AVR plus BIR. Similarly, Is or the sending end current is equal to CVR plus DIR. So from this expression you can see that the transmission line parameter A will be the coefficient of VR when we express the sending end voltage Vs in terms of Vr and Ir. Similarly is the case with B. Here you can see that B is the coefficient of IR when we express Vs in terms of Vr and Ir. And similarly you can get the parameters C and D from this expression. So first we have to express Vs in terms of Vr and Ir. Then from there you can evaluate ABCD parameters. Now let us see how we can write Vs in terms of Vr and Ir. For that we have to refer to the equivalent circuit here. This is the equivalent circuit. Here you can see that this is the receiving end voltage Vr. And here this is the voltage, or this is the point where we have connected we are assuming that the whole line capacitance is lambda, or it is concentrated at this point. So here from this expression you can see that Vc will be equal to Vr plus the drop across this. So Vc can be expressed in terms of the drop across this and the Vr, and Vs will be the drop across this impedance plus this Vc. So you can represent, once you represent Vc, write Vc in terms of Vr and Ir, you can get the expression for Vs in terms of Vr and Ir. Let us see how we can get that. Here you can see that this is the first equation. Vc is equal to Vr plus Ir into Z by 2. Here you can see that we are representing this parameter as, this is actually Z by 2. Those the line resistance and the inductive reactance, we are considering that half of that will be on this side of the Vc, or at the starting point, and this is at the receiving end point. So here you have Z by 2 here also you have Z by 2. So in this case you can see that Vc, if you apply Kirchhoff's voltage law to this loop you can see that Vc will be equal to IR, they draw IR into Z by 2 plus VR. That is the equation, that is the first equation we have obtained here. Vc is equal to VR plus IR into Z by 2. And from this equivalent circuit you can see that IC, this is the point, this is the current IC flowing from this point Vc to the ground. And you can see that this is at a potential of Vc with respect to this point, and this is the admittance. So the current will be given by, either it is given by Vc by Xc, if it is expressed in terms of Zc. But here we have expressed the capacitance, the effective capacitance in terms of its admittance. So the current will be given by V into admittance. Current is equal to, or IC is equal to the voltage VC at the point into the admittance. Admittance is actually the reciprocal impedance. So this will be, here you can see that VC into J omega C, that is IC, that you can get from here also. This is the current IC, and that is the formula we have written here. IC is equal to VC into Y. And from here, and you can see that Is is equal to IR plus IC, because if you apply Kirchhoff's current law at this point, you can see that Is, which is the current flowing into the network, that is equal to the algebraic, or it is equal to the sum of the current flowing out of the node here. Here Is is flowing into the node, and this IC and IR are flowing out of the node. So if you apply Kirchhoff's current law at this point, Is will be equal to IR plus IC. That is the formula we have written here. So IC is equal to, IC is equal to VC by Y, that we have already seen, and Is is equal to IR plus IC, and that is equal to IR plus IC. You can substitute here. This IC comes here. IC is equal to VC into Y. So Is is equal to IR, this IR plus VC into Y, but VC is equal to this one, VR plus IR into Z by 2. This is VR plus IR into Z by 2. So this is actually VC, and Y is here. And if you rearrange the terms in this expression, Vs is equal to, and another equation you can write. This is one equation which can this is one equation which represents Is in terms of IR and VR, and that is, and if you represent Vs in terms of, here you can see that Vs is equal to, from this formula you can see that Vs is equal to Is into Z by 2. Is into Z by 2, which is the drop across this impedance, and the voltage here VC. We have already an expression for VC in terms of VR and the drop across this. So Vs can be written as Is into Z by 2 plus VC. That is this expression. Vs is equal to VC plus Is into Z by 2, and that is VR plus Is is equal to this one. Is is IR plus VR into this expression. So from here you can see that it is IR into Z by 2 . So here Vs is equal to Vc plus Is into Z by 2, and Vc is equal to Vr plus IR into Z by 2. So this is Vc plus Is is IR plus IR into Z by 2. This is actually equal to here VR plus IR Z by 2, that is equal to VR plus IR Z by 2, that is Vc. So this term is actually Vc, and plus here you have, this is the expression for, here you can see that Is is equal to IR plus this expression, that is this expression. This is Is into Z by 2. So Vc plus Is into Z by 2 can be written here like this, and this is the expression for Vc, and this is the expression for Is from here and into Z by 2. Now if you simplify this, you can, our aim is actually to express Vs in terms of VR and IR. So from here Vs will be equal to, you can take VR, from here VR you have 1 plus, if you take VR outside you have 1 here, 1 plus here, this term will be VR into Yz by 2. That is how we are getting this, VR into 1 plus Yz by 2. If we combine this term and this term, plus IR into, you have to find the coefficient of IR here. So first you have Z by 2 here, that's Z by 2 here, and this IR into Z by 2 will come there. So that is this term, and again you have this term is the, so that will be IR into ZY into this. So Z square Y by 4. Z square Y by 4. This term will come there. So we get this expression. If you expand or if you rearrange the terms of VR and IR here, we get this expression, and it which can be simplified as VR into 1 plus YZ by 2 plus IR into Z by 2 plus Z by 2, that is Z, and here we have YZ squared by 4. So finally we get this expression, and that is equal to Vs. Vs is equal to VR into this term plus IR into this term. That means Vs is expressed as a, or Vs is expressed in terms of Vr and Ir. So from the definition of, or from the definition of the transmission line parameters, you can see that this is the expression. Vs is equal to A Vr plus B Ir. So A and B can be readily evaluated from the formula we have obtained. So this will be A parameter, because that is the coefficient of Vr in when we express Vs in terms of Vr and Ir, and this is the expression for B. So in ABCD parameters, we have evaluated A and B. Now you have to find C and D. But in order to evaluate C and D, you have to express IS in terms of IR and VR. And here you have an expression for IS. Here you have an expression for IS in terms of IR and VR. So from here, the coefficient of VR will be Y. The expression will be VR into Y, and the coefficient of IR will be 1 plus ZY by 2. So here, from if you compare, if you this IS can be from here, you can write IS as IS is equal to, from here you have if you take VR outside, VR into, here the term will be VR into Y. So you have this plus IR into, the coefficient of IR will be 1 plus, and here you have a term ZY by 2, 1 plus ZY by 2. You can write it like this. And now if you compare the coefficient of VR and IR in this expression, this will be C and this will be D. That is how we evaluate A, B, C, D parameters. So for easy reference, it is given here. This is the expression for Vs in terms of VR and IR, and this is the expression for Is in terms of VR and IR. And now if you compare, you can see that this is A. Or if you are comparing this with these equations, we get A is equal to 1 plus YZ by 2, B is equal to Z into 1 plus YZ by 4. Here, this is the expression for B, as we have seen in this case. Here you can see that Z can be taken out as a common factor from this B. So Z into 1 plus YZ by 4 will be the expression. So Z into 1 plus YZ by 4, and C is equal to Y, and D is equal to 1 plus YZ by 2. C is equal to Y here, and D is equal to 1 plus ZY by 2. And this you have to remember. These are the ABCD parameters of the medium transmission line if it is represented in terms of, or when it is represented as T parameters. And we have seen that in case of a symmetrical network, and you can see that the transmission line will be symmetric as well as reciprocal. So the condition for that will be equal to AD minus BC is equal to 1 and A is equal to D. This you might have studied when you studied the two-port networks. AD minus BC. If you calculate AD minus BC, these are the expression for A, B, C, D, and if you substitute AD minus BC here, you can see that it is equal to 0, and clearly you can see that A is equal to D. So the transmission line, or the representation of the transmission line in as its T equivalent representation of the medium length transmission line in terms of its T parameters, the transmission line is symmetric as well as reciprocal. These are the conditions for that. AD minus BC is equal to 1 and A equal to D. So these conditions you have to remember, and the parameters or the ABCD parameters of the medium length transmission line also you have to remember as far as examination is concerned. Now if you represent the medium length transmission line as a nominal pi representation. This is the nominal pi representation circuit diagram, and the difference between the nominal t representation and nominal pi representation is that in the nominal t representation we have divided the impedance as total impedance we have divided into two, and half will be on either side. And here what we do is, and in that case in the T representation whole capacitance was assumed to be lumped at the center of the transmission. But in this case, in the nominal pi representation, the line capacitance is assumed to be lumped at both ends, at the sending end and the receiving end, half after considering half of the line capacitance. That means half of the line capacitance will be connected at the starting end, and half of the line capacitance will be assumed to be lumped at the receiving end. So this will be the resulting equivalent circuit, and this resembles the letter pi like this. That is why it is known as the nominal pi representation. So you have to remember this: half of the capacitance will be lumped at the starting end, and half will be at the receiving end, and the whole series impedance or the series or the R plus jx will be lumped at the center of the transmission line, or it will be considered as a whole after without dividing into two, if you compare the T representation and the nominal pi representation. And as we have analyzed the equivalent circuit when we represent the transmission line in terms of its T parameters, here you can see that IC1, which is this current, here you can see that this is the current IC1 flowing through this capacitance, and you can see that the terminal voltage of the capacitor is VR. So the current will be VR into its admittance, that is VR into j omega c by 2. J omega c by 2 is the admittance of this capacitor here, and IL, here you can see that IL is the current flowing in this direction, and that will be equal to, if you apply Kirchhoff's current law at this point, you can see that IL will be equal to IC1 plus IR. So IL is equal to, or this is the Phasor diagram. Once you analyze the Phasor diagram, you can write these equations also. Here you can see that based on this equivalent circuit, the Phasor diagram can be drawn like this. This is the receiving end voltage VR, and we are considering that as reference. And you can see that if you consider VR as reference, IR will be lagging because it's in predominantly inductive circuit. So IR will be lagging with respect to VR here, and you can see that IC1 and IC2. Here you can see that IC1 will be leading by an angle of 90 degree with respect to VR. So if this is the Phasor VR, you can see that IC1 will be leading by an angle of 90 degree. That is why it is drawn like this. This is VR, the voltage across this, and the current through the capacitor, the leading angle will be 90 degree here with respect to VR. Similar is the case with IC2 here. Here you can see that the terminal voltage of this capacitor is Vs. So the current flowing through this capacitor, it should lead by an angle of 90 degree with respect to Vs. So if this is Vs, IC2 will be leading by an angle of 90 degree. This angle is 90 degree. So based on that, you can see that if you apply Kirchhoff's current law at this point, IL will be equal to IR plus IC1. So this is the vector representing IR. That IR plus IC1 is in this direction. So this is IC1. So the resultant vector will be IL. Then IL is the current flowing through this impedance. So here you can see that IS will be equal to IC2 plus IL. So this is IL and IC2 is in this direction. So it will be drawn like this. This is IC2. So IL plus IC2 will give you IS. And it is evident from this equivalent circuit also. And here you can see that from this you can see that so here you can see that Vs is equal to this. We have already seen IL is equal to IR. That can be obtained from here, because here you have IL is equal to, IL is the vector sum of IR and IC1. So IR can be written as IR cos phi R minus J sin phi R, because IR into cos phi R minus J phi R, because this is the angle phi R, and the x component will be positive and the y component or the imaginary component will be negative. That is why we have taken negative here. And plus j VR omega c. This is the expression for IC1 that we have already seen. So IL in terms of IR and VR is this expression. Similarly, Vs is equal to this is the point where we have the voltage Vs. So the Vs will be equal to the, or if you apply Kirchhoff's voltage law to this loop starting from this point to here. And you can see that this is the voltage Vs here, and the drop across this is IL into Z, IL into R plus Jx by 2, and the voltage between these 2 points is VR. So the resulting equation will be Vs is equal to IL into Z plus VR. That is Vs is equal to VR plus IL into Z, and here you have VR here, and the expression for IL here we have the expression for IL that will be substituted here, plus that into Z. Z is R plus Jx from here. So this is the expression for Vs in terms of VR and IR. Once you get an expression for Vs and VR, you can evaluate the regulation. And for Is, you can see that Is will be equal to IL plus IC by 2. So Is is equal to IL plus VC by 2. Sorry, IC by 2. Sorry, Is is equal to IL plus IC2. IC2 is the current flowing like this through this capacitor. So that will be equal to the terminal voltage is Vs here, Vs into its admittance, Vs into j omega C by 2. Vs into j omega C by 2, that is IC2. So Is is equal to IL plus IC2. And IL can be, so IL can be substituted with this expression, that is IL here, IR into cos pi r minus m. This is the expression for IL here, plus j omega C by 2, and this is the expression for Vs. We have an expression for Vs in terms of VR and IR. That is the expression here into R plus Z by 2. So JVC into JVR, this is the whole expression is the representation for Vs, this Vs. So we have obtained the two relations which represent Vs and Is in terms of VR and IR. And in order to find VR dash, actually we have to know the no load voltage at the receiving end, that is the VR dash. And at the receiving end, if you have no load current IL, so in that case, so in order to calculate the regulation of the transmission line, we have to find the VR when there is no load on the transmission line, which is designated as VR dash. And you can see that when there is no load on the transmission line, the only charging current will be there. This IC1 will be there, and if you find the voltage across the capacitor at that point, that will be VR here. So the equivalent circuit will be something like this. Here you can see that Vs is available at this point, because the potential, even though some current will be flowing through this capacitor anyway, it won't be affecting the terminal voltage at this point. So here you have the voltage Vs. In between these 2 points, you have this voltage Vs. So the equivalent circuit will be Vs connected with a series combination of this impedance and this, and we will be taking the potential difference across these 2 points in order to get the no load terminal voltage. So this will be the equivalent circuit of the nominal pi representation when there is no load on the transmission line. So here we have Vs, the magnitude of Vs will be here. Actually our aim is to find the magnitude of the terminal voltage when there is no load on the transmission line. Only the charging current will be there. So this is the impedance Z, and this is the capacitance connected here. So the equivalent circuit will be Vs will be connected here, and the current will be flowing through this, and we will be finding the potential difference between these 2 points. And if you redraw the circuit, it will be something like this. So, and from here you can see that the total current flowing through the circuit will be Vs divided by the series combination of this, that is VR dash, which is the terminal voltage across the capacitor C. That will be the total current flowing through this into this impedance. Total current flowing through this is Vs divided by R plus Jx minus j omega C by 2, which is the series combination of this resistance and these reactances into this impedance or this reactance, that is this one. So this will be the expression for VR dash. Once you get VR dash and VR, the expression we have already evaluated here. The expression for VR and Vs, we have Vs and Is in terms of VR and IR we have already calculated. Once you know VR and the no load terminal voltage VR dash, you can evaluate the regulation. And this is the same formula which we have used in case of T representation for calculating the percentage efficiency. The P divided by P is the three phase power transmitted over the or at the received at the receiving end, and L, the R is the resistance of the transmission line, per phase resistance of the transmission line, and you have to multiply, and IL square R will be the total losses occurring on the transmission line, because the real power will be dissipated only in R. So I square R, IL square into R you have to consider. This is IL, that IL square into R will give you the total power dissipated at this resistance. So once you know, and we have to consider three. If we are considering the three phase power, you have to consider the three phase losses. That is why a factor of 3 is coming here. So this is the expression for the efficiency of the transmission line. And in order to evaluate the ABCD constants or ABCD parameters of the transmission line, when we represent the medium length transmission line as its nominal pi representation. These are the expressions we have already seen. IC1 is equal to VR into Y by 2, because the representation is something like this. So this is the nominal pi representation. You have the whole Z connected. This is the Z, and this is you have Y by 2 connected here. This is the admittance by 2. Here you have admittance by 2. And this is the nominal pi representation. And here you have Y by 2. Here you have Vs. Here you have VR. And you can see that this is IR. This is IS. Sending end voltage, say let this be IC2, let this be IC1. So from here you can see that IC1 will be equal to, this is the terminal voltage or the voltage across this capacitor is VR. VR into its admittance, Y by 2 will give you IC1. So IC1 is equal to VR into Y by 2. That is the expression we are getting here. IC is equal to VR into IC1 is equal to VR into Y by 2, and IL is equal to IR plus IC1. IL is equal to IR plus IC1. This is IC1 and this is IL. You can see that if you apply Kirchhoff's current law at this point, IL will be equal to IC1 plus IR, the receiving end current. So we are getting this expression. IL is equal to IR plus IC1. That is IR plus IC1 we have already calculated like this. So IR is equal to VR plus VR into Y by 2. Now IS is equal to IL into IC by 2. That can also be clear from here, because if you apply Kirchhoff's current law at this point, this is the current IL flowing. So IL is flowing out, and IL is flowing out, IC2 is flowing out, and IS is flowing into the network. So if you apply Kirchhoff's current law at this point, IS is equal to IC2 plus IL. IL is the current flowing through this impedance. IC2 is the charging current or the current flowing through this capacitance. And here you can see that IC2 is equal to IC2 in between the capacitor, at the terminal of the capacitor you have a voltage of Vs. So Vs into admittance will give you the current flowing through that. So IC2 will be equal to Vc into Y by 2 plus IL. Sorry, IL here. This is the expression. IS is equal to Vs into Y by 2 plus IL. So we are getting this expression IL is equal to Vs into Y by 2, and we have already seen IL is equal to IR plus VR into Y by 2, that we have already seen. Plus you have Vs, expression for Vs as VR plus, that can be obtained from here, because Vs is equal to VR plus IL into Z, that is clear from here. Here you can see that Vs, that is the potential between these 2 points, that is equal to the drop across this plus this voltage. So the drop across this is IL into Z. IL into Z is the drop across this impedance. So Vs will be equal to IL into Z plus VR. Now you have an expression for IL in terms of IR and VR. So that can be substituted here. Here you can see that Vs is equal to Vr plus IL z by 2. That is Vr plus IL. We have IR plus Vr into y by 2. This is the expression for IL which is obtained from here. That into this z is here. So if you rearrange the terms, Vs is equal to Vr into, here you have Vr into 1 is there, and here you have a term Vr into yz by 2. So we get this 1 plus yz by 2 into Vr plus coefficient of IR here is z arrow. So this is Vs is equal to 1 plus yz by 2. So this is an expression for Vs in terms of Vr and IR. And here Is is equal to IL plus Vs by 2, like this. Here you can see that IL is equal to IR plus VRY by 2, that we have already seen. And this Vs is this expression. Vs is equal to 1 plus Yz by 2 into Vr plus ZIR. That is this expression into Y by 2. This Y by 2 comes here. That means we have an expression for Is in terms of IR and VR. Now we have to rearrange this. So VR into the coefficient of VRR y by 2, here 1 y by 2 is here, and here you have here also you have a term VR into y by 2 if you multiply this term. So VR into y we get, and another term is VR into this term will be there yz by 2, and that will be again multiplied with this. So it will be y square z by 4. That is how you are getting this. Now the expression for the coefficient of IR is, here you have 1 here, 1 plus. Now here you have IR into zy by 2, because this will be ZIR into y by 2. So 1 plus yz by 2 IR. So this is the expression for Is in terms of VR and IR. That means if you compare the original equation, Vs is equal to AVR plus BIR, this will be the expression for A, and this will be the expression for B. Similarly, Is in terms of VR and IR, so this will be the expression for C. That is, C is, if you take Y as common factor here, the expression will be Y into 1 plus YZ by 4. So this is C and this is D. So you can get the expression for A, B, C, D parameters when the median length transmission line is represented as a pi representation, or as its nominal pi representation. So you have to remember these A, B, C, D parameters for the Y representation and for the T representation. Here also you can see that the transmission line will be symmetric as well as reciprocal by applying these conditions. AD minus BC will be equal to 1, because AD minus BC, you can substitute these values and calculate the expression AD minus BC, and you can see that it is equal to 1. Similarly, the A is equal to D. The expression for A is the same as expression for D. So these two conditions, AD minus BC is equal to 1 and A is equal to D, proves that the transmission line, it is symmetric as well as reciprocal.